Hi everyone. Today we're going to be talking about Ohm's law and Kirchhoff's current law and how they pertain to circuit analysis. So let's get right into it. So this is what we're going to be doing today. We're going to go over Ohm's law, we're going to go over a short example, and then Kirchhoff's law, and another example for Kirchhoff's law, or KCL. So let's go over some basic definitions. So first let's go over what current is. Current is what is called the time rate of change of charge. So essentially this is measured in coulombs per second. So how much charge is flowing through the circuit at any given time. So and coulombs per second, 1 coulomb per second is equivalent to 1 ampere, and current is measured in amperes. Resistance is basically the amount of resistance an electron encounters as flowing through a circuit. As electrons move through materials, they collide with the atoms and lose some of their energy. So there is a so-called resistance to current flow, And the value of resistance depends on the material used, as well as the cross-sectional area and the length. For example, copper has a very low resistance and is a good conductor, and glass is a very good insulator and thus has a very high resistance. Voltage, or the electromotive force, or EMF, is a measure of work required to move 1 coulomb from one point to the other. For example, between battery terminals. Basically, it's the amount of energy to move 1 coulomb from the positive terminal of the battery, or technically from the negative terminal of the battery all the way to the positive terminal. Or the other way around, Now let's get on to Ohm's law. So what is Ohm's law? As resistance exists, Ohm, a scientist, measured and described the relationship between voltage, current, and resistance. Specifically, Ohm found that the voltage drop across any linear component, a linear component is a component that follows Ohm's law. The voltage drop across a linear component is directly proportional to the current flowing through it. And this is described by the equation V is equal to IR. And this equation can also be rearranged to I is equal to V over R, or R is equal to V over I. Now that we have this information, let's move to the iPad and let's talk about it a little bit more, and let's do a problem. Now, on the iPad, let's say, before we go to the problem, we can talk about an example. Let's say we have a resistor R, and there is a current flowing across it. Now we can basically take 2 points, point 1, point A, and point B. Now we can find the voltage at point A and point B. And now we know we could write that V is equal to V1, or VA, minus VB. And that VA minus VB is equal to IR. So this is just an example of how we could use Ohm's law and how Ohm's law is used. Now if we find that actually VB over here is greater than VA, V would be negative, so would I. And that's just so, and thus, if I was negative, it would actually flow the other way. And that is the conventional way of how we would use Ohm's law and how nodes or points are used. Now let's do a quick problem. So we have this problem. Question number 1. An electronic device that you are designing requires a component that has a maximum current rating of 50 milliamps. If a resistor of 250 ohms is placed in series with the component and has a voltage drop across it of 10 volts, will the component still work? What if the resistor was 100 ohms instead? So let's draw out this problem. So we have some kind of voltage source, and that is just connected like this over to a resistor, and that is connected to some component, right? And we don't know what that is. It doesn't really matter. So this is a 250 ohm resistor, and the voltage drop across it is V. V is equal to 10 volts. Now let's do an Ohm's law analysis on this. Right? So now we know that R is equal to 250 ohms. And now with these two we can calculate I, right? So we know V is equal to IR, and thus I is equal to V over R. Now, what if we do I is equal to 10 over 250? What is that equal to? Well, boom boom, that would be 0.04 or 40 milliamps. Now we can answer this question. Would the component still work? And we know that yes. For part A, yes. The component will still work. And now for part B, if R was actually 100 ohm, what would I be? Well, we just do the same exact thing. V is equal to IR, I is equal to V over R, which is equal to 10 over 100, right? Cancel out, and we're left with 0.1 amps, which is equal to 100 milliamps. So for part B, the answer would be no. It would not work. So that is an example of how we would use Ohm's law. Now, let's move on to discussing Kirchoff's current law. Right? So, what does Kirchoff's current law state? Kirchoff's current law essentially states that as charge is conserved in the circuit, the sum of currents entering a node or a point in the circuit or a junction must equal the sum of currents exiting that node. In simple terms, that basically just means I in is equal to I out. In this example that we have on the right, we have two currents entering, I1 and I2, and that is equal to the two currents exiting, I3 and I4. So this is very simple, right? And let's move on to the iPad to kind of discuss it a little bit more. So over here, we can have a few examples. For example, let's say we have something like this. We have like 5, maybe 6 currents entering. And we could label everything. Right, so we have I1, I2, I3, I4, I5, I6. And let's just put arbitrary directions on them. 1, 2, 3, 4, 5, 6. Right? This diagram basically means that the sum, remember, Kirchhoff's current law says sum of I in is equal to the sum of I out. So in our specific case here, it would be I1 plus I3 plus I4 plus I5 is equal to I2 plus I6. So that's how we would use it in this example. Now let's do an actual problem with it. So we have this problem. Question number 2. Find I1, I2, and I3 if IA equals 8 amps, IB equals 7 amps, and IC equals 9 amps. Now, let's start. So let's draw out the circuit. We have branch going like this. Let's make a big rectangle. Have a branch coming out like this. Have one like this. And we have these two that connect down. Alright, so now that we've drawn out the circuit and we have our given, so this is given, IA is equal to 8 amps, IB is equal to 7 amps, and IC is equal to 9 amps, we can begin. So let's label some nodes. We have node A, we have node B, and we have node C, and we have node D. And basically these nodes are all just junctions, right? So a node is a junction. Now let's do KCL at A. What do we have? Well, remember, I in is equal to I out, right? So we have coming in, we have IB is equal to going out, right? We only have IB coming in is equal to IA plus I1. Now, next we have KCL at B, which is just coming in is I1 and I2, right? So I2 kind of comes like this. I1 is equal to I1 plus I2 is equal to I3. Simple. Now at KCL at C, what do we have? Coming in, we have IC. Is going out, we have IB plus I2. Finally, we have KCL at D. Coming in, right? Because we have IA. IA goes all the way around, right? So we have IA plus I3 is equal to IC. Boom. Now we can plug in all the constants, IA, IB, IC, and we can solve. Right, so we have three equations, 3 unknowns, and 4 equations. So this is very solvable. So let's plug this stuff in. So beginning with the first equation, right? So we have equation 1, equation 2, equation 3, equation 4. So let's begin with equation 1. We have IB. IB is, remember, 7 amps. So we have 7A is equal to 8A plus I1. And we could just solve for I1, right? I1 is equal to 7A minus 8A, which is equal to -1. So we solved for I1 already. Boom. Equation 2. We have I1 plus I2 is equal to I3. And we can plug in I1 from earlier, so -1 plus I2 is equal to I3. So we can leave equation 2 as it is. Now we can move on to equation 3. Equation 3 is IC is equal to IB plus I2. Now we can plug these things in, right? So we have 9A is equal to 7A plus I2, and we could just solve for I2. I2 is equal to 9A minus 7A, which is equal to 2 amps. And equation 4. Equation 4 states that IA plus I3 is equal to IC. IA plus I3 is equal to IC. We have IA is 8A plus I3 is equal to 9A. And we can say that I3 is equal to 9A minus 8A. I3 is equal to 1 amp. And to confirm, we can plug all 3 in equation number 2. Right, so we remember equation 2 was simply I1 plus I2 is equal to I3. We know that -1 plus 2 is equal to 1, and that just checks out, right? 1 is equal to 1, checks out. So we have solved it. We found I1 is equal to -1, I2 is equal to 2, and I3 is equal to 1. So that was problem number 2, and that was everything that we have today. Thank you so much for watching, and yeah, that's it.